Hi again, my name is Andre DeVilliers. I work at Ericsson, working with Wincom as our channel partner. And this is my second webinar for this audience. And today we wanted to talk about the Ericsson Multiband Booster, which is a solution that we have that utilizes a number of parts of our microwave radio portfolio that provide some very compelling solutions and ultimately some cost-efficient ways to increase microwave capacity. So we'll jump right in. The agenda set of topics for today are here. We're going to talk about what is multiband booster, what are the the basics, and what are the building blocks that kind of make this solution put this solution together. We're going to talk about how we implement it in MiniLink, which is our microwave radio portfolio. We're going to talk about dual band antennas, those that are capable of carrying traffic on two different frequencies. We're going to talk about the benefits of the multiband booster solution, and then a summary at the end and some information about how you can get more information or how you can get going working with your Wincom reps and moving forward to bring these solutions to your customers. Okay, so this session is not necessarily intended to be a primer on the Ericsson MiniLink portfolio. We've done that in other forums, and we can do that again for anybody that's interested. But as a refresher, the portions of the multiband of the MiniLink portfolio that are relevant for multiband booster are basically our split mount and all outdoor radio solutions. So just as a refresher, the split mount solution is called the MiniLink 6600, which contains, Elaine, can you tell me if my audio is okay? I'm getting a message that it's not.
You know what, it's cutting out a little bit. You're okay now, though. And actually, no, Andre, we did lose you. Let's give Andre just a moment to work through his audio issue. We'll be back with you as soon as possible.
Okay. Okay.
You're back.
I got a message. Yeah, I got a message that I lost my audio for some reason. So anyway, I apologize for that. The MiniLink 6600 is our split mount solution, and it is shown by the chassis here on the left. That provides kind of the baseband functionality that will be part of multiband booster. The radios may be the MiniLink 6363 or 6365. In combination with one of the outdoor short haul solutions, either the 6352 E-band product or maybe even the V-band product 6351. We also have the opportunity to do this in an all outdoor, like everything outdoor capability with the 6366 baseband. And I'll explain what all of this is as we go. So what are the components of multiband boosters? So first of all, if we start on this slide here, on the left, we see a slide that some information that I presented in my last webinar that showed what Ericsson's estimations were for backhaul capacities of different site types, rural, suburban, urban, kind of over the next few years. And this was in conjunction with 5G deployments and the increase toward 5G. But the long and the short of it was that one of the things that happens with 5G and certainly with any communication solution is that capacities and consumption increases over time. So we're talking about in the worst of cases, situations where urban sites will need hundreds, if not a gigabit, up to 20 gigabits of capacity, depending on the radio configuration. Now, of course, some of those higher end sites are going to be wired with fiber, but fiber can't reach everywhere, and part of 5G is the densification of sites. So there's more and more places to connect with backhaul. So not all of those can get fiber. We need to have wire to complement that. And those sites, of course, will see increasing capacity needs. So on the right side, discusses a little bit about spectrum, which is the primary component for increasing capacity. And you can see from going from left to right as we increase in the frequency band. These are primarily different microwave radio bands throughout the world. As you see going down, you see different regions of the world. The size of the circle kind of indicates the popularity, if you will, of that band for backhaul. And this is dictated by, typically by regulation and how the, in the US case, the FCC or Industry Canada in Canada, or, other government entities kind of allocate that spectrum. So for example, in North America, or at least in the US, for 6 gigahertz, you only get 30 megahertz per channel, whereas in 11 and 18, you can get up to 80 megahertz per channel. And then up in E-band, we have as large a channel as 2 gigahertz. So generally, as you go from lower frequencies up to higher frequencies, of course, your distance is limited, but you also have more and more spectrum that becomes available as a general statement. So what that does is for different regions, customers or operators of these links will have favorites. We'll kind of have a pecking order, if you will, of the spectrum that they want to use first, and others that they don't. So one of the biggest benefits of multiband booster is that it takes away some of that preference, and that you start to combine bands in ways that will ultimately help utilize all the bands. And I'll describe that as we go. Okay, so what is multiband booster? It's effectively a way to combine the capacities that the capacities of multiple bands. And of course, if you've been in microwave radio for a while, then you know that higher bands are not going to have nearly the range that lower bands are going to have. But we kind of use that to a benefit. So we say that the lower band ultimately provides the range of the composite link, but the higher band provides the max capacity of that composite link. So in a way, you get the best of both worlds. You may have a lower availability at the higher band, but you won't lose the link completely because you have the lower band to keep it alive and to keep traffic flowing. And if you pair that with a good way of assigning traffic to those links, then ultimately you can serve your customer best by making sure the most important traffic is carried when you have rain conditions or other things that may fade a microwave link. So what does it enable? We talk about boosting capacities because we're using more and more spectrum. We're going to boost the hop length as well because we may be using the capabilities of a lower band to help stretch a higher band. What I mentioned before about utilizing all spectrum, we're boosting spectrum use. That's another capability here. And then minimizing the total cost of ownership, because ultimately one of the ways to get the same amount of capacity, if you didn't have multi-band solutions, was just to stack more and more channels on lower bands. And that becomes very expensive, if you start to build 2+0, 4+0, 8+0 sorts of links. Every one of those radios, adds costs, where if we can stack them with different bands, then we achieve the same aggregate capacity for a much less cost. This slide kind of shows a number of things. It's very interesting because it kind of shows what some of the better combinations are for a multi-band solution. So the green band, if you will, shows kind of the difference between a mild climate and a severe climate for the range of different bands as you go. And then the blue band, and I'm sorry, and the green band is the 5 nines availability. So that's kind of your typical telecom standard where you engineer a link for no more than 5 minutes of outage a year. Whereas if you stretch that availability to 3 nines, you know, this is more on the order of like 1.8 days, I believe it is, of outage over the course of a year. So if you stretch that, then of course you're going to see, you know, the ability to, you know, stretch distances and things like that. But what you do here, and I'm sorry, this particular graph shows attenuation as you go higher in frequency with a real dip at 60 gigahertz, and that some of you may know is like where oxygen absorbs you know, these radio waves, and so there's a real attenuation around 60 gigahertz. But when you get out of that into E-band, into that 70, 80 gigahertz range, then you kind of have a more predictable attenuation. So what this shows is some different combinations that work really well. And you know, the first one maybe on the top would be to show like a lower band, a 6 or 11 gig in combination with a higher band like 23 or 38 gig. Whereas the other one on the bottom shows kind of that 18 or 23 gigahertz in combination with E-band. Most of what we're going to talk about today is the latter, because E-band really provides a lot of spectrum and a lot of capacity potential. But we will refer to some possibilities of pairing kind of that low and mid-band spectrum as well for multiband solutions. Okay, so the different building blocks for multiband, obviously the first one would be the new spectrum and the new spectrum channel spacings that are available. As you can see on the left, and you know, now these are ETSI figures. So for those of you that may have worked in markets outside of North America, you may recognize these channel spaces: 28 megahertz, 56 megahertz, 112 megahertz. Whereas in the North American markets, that's going to look more like you know, 10 megahertz, 30 megahertz, 40, 50, and 80 megahertz. But in the E-band, the allocations are similar across different markets. So 250, it's usually 250 megahertz chunks up to 2,000 megahertz in this case. That's the first building block. The second one is adaptive modulation, and that's been around for quite a while, obviously, with microwave networks. But when in the context of multiband solutions, it's important to know that each one of those bands adapts independently. So different combinations of capacities can come out of the aggregate of the two bands. The third building block is quality of service. And that's where we kind of assign priorities to different packets in traffic, but furthermore, to be able to assign those packets based on priority to one band or the other. And where this is important is if you do have a mix of traffic that has a kind of a committed amount of traffic, a committed information rate that you need to carry, then try to assign that obviously to the lower band that has the higher availability. Or conversely, for your peak information traffic, then that gets assigned to the higher band because that's where the capacity is, and then that can be a little more sporadic in terms of availability. So that's you know, you use quality of service in combination with that. And then the final building block is really the bonding of links, and that's the ability to take multiple radio channels and then present them to the WAN interface as one single fat pipe effectively. And we can do that in a number of different ways. But Ericsson was the first to introduce and actually has you know, a technique called radio link bonding, which is a highly efficient way of bonding those links to where you can get 99 to 100% of the traffic that you put into it. Okay, so this is a kind of a different way of looking at it, just a way to keep in mind about availability. If you look at how microwave links have evolved over time, starting at the bottom, we had just fixed modulation. Before the days of adaptive modulation, we had a fixed modulation such as like 128 QAM, and if you paired that with 30 megahertz channel, you knew you were going to get I'm just making this up, but let's say 120 megabits per second. I don't know what the number is off the top of my head, but that was basically what you had to work with, and there was no changing that because it was a fixed modulation. In the days of adaptive modulation, now we're taking advantage of the variability of of radio conditions, whether it's rain attenuation or multipath fading or different. Those things change over time, and some days and some conditions are better than others. So instead of just continuing to operate at 128 QAM, we can boost that to 256 to 512 and on up to 4096 QAM, which has their associated capacity increases. So that means that here within 365 days of the year, all except for the last 30 minutes perhaps, that we're able to operate at a much higher capacity with adaptive modulation than we were at the fixed modulation. So as we kind of progress even further than that, now we can do that in two bands, so the low band and the high band, and we show that we have this lower band, which is adaptively modulating on its own, providing a base of capacity, with the high band, which is going to have a lower availability, potentially as low as 2 nines and a 5, which is 1.8 days. Sorry, the 3 nines was 8.8 hours of unavailability. But at any rate, we're looking at, even in this worst case 99.5, you're still looking at all but 2 days of the year where you can operate at the capacity that the higher band is giving you. So that's something that you should definitely take advantage of, and the technology allows you to do that. So a couple of examples of combining, different bands. I'll start at the bottom here again. 7 and 18 gigahertz with their various channel sizes could give you up to 2.5 gigabits per second plus 10 potentially, so 12.5 gigabits per second. And then here, and then that's over 20 kilometers distance. So 18 gigahertz is never going to go 20 kilometers on its own and provide you that on its own. But with that lower band to bolster it, you can get that 20 kilometer distance and then get those peak rates from the 18. So similarly, kind of an example of a mid and a higher band, 15 and 38 gigahertz, with their respective channel capacities, this could give you like a 1.8 gigabits per second. This is just with 2 radios, by the way. You could still potentially stack 2 15s and a 38, or whatever combination you need. And then finally, what's really of interest is where we take a mid-band spectrum like 23 gigahertz, and its channel capacity, maybe providing a gigabit or up to 2.5 gigabits in this example, with an E-band solution with its large channel and up to 10 gigabits per second. So now we're talking about multi-gigabits, up towards 10 gigabits per second, over 8 kilometers. That might be something that 23 can do, at one availability, but now we're talking about 10 gigabits per second over 8 kilometers. That's a very compelling solution. And I've got some other examples from a real customer here that I'll show later. So speaking of customers, one reference that we have here is from T-Mobile in Poland. And in Poland, they were very progressive about licensing and regulating E-band. And with E-band, they it was very inexpensive. Similarly, in the U.S., it's a lightly licensed spectrum, so it's very inexpensive to add these E-band links. But this was an early example 2-3 years ago in Poland, where the customer recognized the opportunity that the regulators were giving them with E-band, and they started deploying E-band links on their own for backhaul but then started effectively stretching the range of E-band by using that in combination with a lower band in the multiband booster configuration. And this is a customer's quote, basically saying that it's so much more efficient and cost effective than stacking radios in the traditional XPIC configurations, which would be 2+0, 4+0 in both polarizations. Okay, so a few details about how we implement it in Minilink. I'll try not to get too detailed here, but certainly if you have questions, ask them, or make note of my email address so we can discuss them, in whatever depth you need. Okay, so multiband booster in Minilink will require a kind of an indoor unit or a switch. Basically, the value of the indoor unit is the layer 2 switch that comes with it, and that helps with some of the boosting functionality. Also, the indoor unit has modem cards, so these radios terminate to a modem card via coax, and the modems themselves do radio link bonding. And then there's the switch that's embedded is on a card called the NPU that also plays a role in some of the multiband booster. Similarly, with the 6366, that's basically just an outdoor IDU, indoor unit. It's just in a hardened case, so you can see it in the back of this, but it also provides the same sort of functionality. So starting with radio link bonding. That's effectively just the ability to take, multiple streams and then aggregate their capacity over one fat pipe. Now, this may be implemented with 2 radio channels in this case. So this is just a simple example of maybe a 2+0 link in the same frequency. So let's say 2 18 gigahertz links. That aggregate capacity that's coming from these 3 sources is mashed together through the indoor unit, and then presented out toward 2 radio links, as one fat pipe. And, the reverse is done on the other end. Now, that radio link bonding actually happens in the modem. So that the MMU 1002 is the modem plug-in unit that goes in our indoor unit. And it's capable of doing this bonding across 2 radios, to 2.5 gigabits per second. Basically what the radio can do. Now, one modem can actually work together with another modem as a kind of a pair. So actually 4 of these radios can be bonded together up to 2.5 gigabits per second, just with the capabilities of the modem. Another way to do this is with the 6352, the E-band radio actually has an embedded layer 2 switch inside of it, and those can talk to each other all by themselves without an indoor unit and do radio link bonding to provide, in this case, up to 10 gigabits per second. But if each one of these is operating at 5 gigabits per second, then you can present one fat pipe as 10 gigabits per second to the traffic interface on one of these radios. Elaine, can I get a quick sound check? My app seemed to just give me a different change, but it looks like I'm still presenting, right?
Yes, it sounds okay right now, so you're good.
Yeah. Thank you.
Mm-hmm.
Okay, taking it up a notch, the modems present traffic to the switch in the backplane of the indoor unit, and we do something called hierarchical radio link bonding within the NPU. And so that's now taking it up a level and being able to potentially bond multiple bonded channels. So in this case, we can stack up enough to get to 10 gigabits per second, which coincidentally matches the 10 gig port that we have on the NPU. So I'll kind of keep it at that level for now. But there's implementation details here that we can certainly talk about if you have questions. And then finally, we have a feature called policy-based forwarding. And that is taking the QoS, as I described before, the QoS features of the layer 2 switch, and being able to assign that traffic type to multiple WAN ports. And then in this case, the WAN port is the radio. So again, take your peak traffic and send it toward the E-band, where you're going to have lower availability but higher capacity, and then your committed traffic and send it toward the lower band, where you're going to have higher availability but lower capacity. And that's the idea there. This is a little more detail on the types of policy-based forwarding we have. Basically, strict priority, or strict priority with a dynamic VLAN handling. These are just two examples of kind of how that works, but I won't get into that. Let's see, it looks like I might have a question here. Oh, there they are. Okay, question is there benefit of combining 6 or 11 gigahertz with 80 gigahertz? Unlikely. And the reason is that now you need to have some availability at 80 gig. And if you're using 11 or especially 6 at the ranges that those are designed for, then you're probably not going to have much of a signal at 80 gig. As I'll talk about the dual band antennas, we build our dual band antennas based on likely combinations, and we see more of an opportunity for like 18 with 80 or 23 with 80. And then maybe for 6 and 11, maybe those are combined together, because there's a lot of congestion at 6 gigahertz. So being able to take advantage of 11 on the same link, is a nice solution. Or maybe even 11 and 18. Those are probably more appropriate. That's the only question I see. So I'll move on. Okay, here's another customer reference from Hrvatska in Croatia. It's a subsidiary of Telecom Austria, basically, A1 Telecom Austria. And so this is a company that was seeing its microwave backhaul capacities increase. They started by using bonded multi-channel XPIC, like I described before. Like let's say they had 4 channels of 600 megabits per second. You could still bond those to get you 2.4 gigabits capacity, but now you're doing that with 4 radios, and you're doing that with, if you want to do that over 1 antenna, then you've also got power splitters and OMTs, and something that can be very complicated, and certainly very heavy on the tower potentially, and costly to install. So again, in Croatia, the regulations around E-band were favorable. So being able to build E-band in combination with one of those links was going to provide the same amount of capacity with for this customer. So that solved some issues. And actually, according to the reference here, it says that they were able to provide up to 10 gigabits per second with low TCO, including licensing fees. So now that's kind of their standard, is to roll these out. Okay, dual band antennas. So again, that'll come in different varieties, but the idea is a single antenna that provides you an interface for 2 different bands, and those interfaces will come in different types. The first one is where we see up to 2 lower bands in combination with an E-band. Okay, so in this case, it's actually 2 23s plus an E-band, and this would provide, in this example, up to 10 gigabits per second over 8 kilometers. I'm sure that's very good conditions, radio conditions for 23 gigahertz, but this is doable with the multiband solution. And then finally, more kind of your low band and high band. Here's an example of 7 gig, which is not a frequency for North America, but you could say 6 potentially here, and 18 gig, where this was providing up to 10 gigabits per second in 20 kilometers. So, and this is with just a single, oh no, this is a stacked solution where there's 8 of these and 4 of these. So there would be a few more of these, but it's still, this actually relieves a different sort of problem where you, especially like in 6 gigahertz in North America, you only have 8 channels with 2 polarizations, but you only have that to work with. So if you need to expand an existing link, you want the dual band antennas to be able to, not add too much tower footprint while still adding capacity. So this is actually the different sorts of dual band antennas that we provide. Starting kind of on the top left here, we have HP basically is a high performance antenna, but it's single polarized. You also see HPX, which means dual polarized high performance antenna. So in the HP example, it's a single channel of E band in combination with a traditional band. 18 and 23 are 2 that come to mind that are already released. And we also can do a dual polarized traditional band with a single polarized E band. So that's HPX for the traditional and HP for the E band. Taking it to the next logical conclusion here, we can do dual band in traditional and dual band in E band. So that's HPX. And this, if each one of these traditional bands is capable up to a gig each, and these are 10 gig each, this potentially could drive 22 gigabits per second in this footprint, which is not bad at all. And then finally, if you had 2 different traditional bands, HPX, we could actually do kind of a 4+0 on a single polarized, single antenna solution. So one more customer example. So we've been working with a number of these CAF funding winners. I think the current program is called RDOF for rural broadband. So there's a number of funding initiatives that the government is providing to encourage internet service providers and operators to start serving rural underserved regions, typically in rural America. And this customer is deploying Ericsson CBRS radios for the access. And of course, they're going to need microwave backhaul in a lot of locations. So these rural links are typically going to be longer in range, and but these operators aren't necessarily operating at the 5.9 standard, right? So they're willing to, because anything is better than nothing, or a lot of times whatever you're providing is better than HughesNet or some other solution for these rural customers. So, in this case, they're willing to live with links at 8 kilometers at 3 nines, for instance. And then, of course, it's, as I've described, it's a smaller footprint than a 4+0 or 8+0 configuration, providing the same capacity. So in this case, this is a case where we're just using one E-band radio with one 18 gigahertz radio. And, each of these channels, and I kind of cut this off to not show the lower capacities, but, we can adapt all the way down to 4 QAM in the 18 gig. And then this is pretty much the range for the E-band from BPSK to 128. But you can see the 3 nines point comes at, and this is a 3 nines composite, comes at 2 gigabits per second. And this is 8 kilometers in this particular case, 2 gigabits per second. But this is, the 3 nines level. So during those 363 days of the year where your availability, where you're not having these fading conditions, you can actually adapt up all the way up to 10 gigabits per second potentially. Realistically, probably more like 6 or 7 gigabits per second. So that's very compelling, very future-proof sort of solution for a customer like this that, has an opportunity to grow their business. So a little bit on benefits. Let me check if we have any other questions at this point. I don't see any. Elaine, am I missing any questions? Don't know.
Yeah, there's actually two. Do you want me to read it off to you?
Yeah, because it's not, it's kind of cut off here. So if you don't mind.
Mhm. What's the typical antenna size you use with the 18 gigahertz links?
So that dual band antenna comes in two sizes, in 1 foot and in 2 foot. So either one is available.
Okay, and then just one other question. Are
Mhm.
there installation guides available?
Yes. Yeah, for sure. We have a lot of documentation that Wincom already has available to them, and of course, we make that available to Wincom and all of their reseller customers. You may be referring to or maybe somewhere in those questions is the fact that a 2 foot antenna. The other thing is that as you go up in frequency, the beam widths start to get very, very narrow. So especially at E-band, we're talking about beam widths that are very, very narrow, inside of 1 degree, especially for a 1 or 2 foot antenna. So aligning those antennas becomes very difficult. But we do have tools to help that become easier. Okay. Oh, multiband booster benefits. Yes. So kind of leading to our summary here, but of course, we can boost capacities, boost stop length, utilize spectrum as much as possible, and minimize TCO. So we're talking about, in this case, a 23 plus 80 solution where we're delivering potentially up to 10 times the capacity of what 23 would have done by itself at 3 times the distance. So you're really getting the best of both worlds here for very little footprint cost and 1 extra radio. TCO, this effectively that point here. So, in a typical world, if you were to stack 4 channels of 23, you're talking about, the CapEx for 4 radios. And then those 4 radios need a way to effectively multiplex onto the same antenna. So those sort of solutions, whether it's a power splitter or an OMT or any other sort of channel aggregation solution, becomes very heavy from a CapEx standpoint and from a weight standpoint that sit on the tower. If you can do that with fewer radios and 1 antenna, then that becomes the best solution of all. And so our estimate, if you're interested in the what's behind these numbers, I can provide those afterwards. But our estimate has been 45 to 75% savings in spectrum cost. Of course, that depends on the particular regulations of your area, and then product cost about 35% savings. And this is speaking toward the example earlier where we talked about congestion and 6 gigahertz. So if we need to increase capacity beyond the channels that are available there, then this, of course, gives you an opportunity to increase capacity on those particular solutions. So by adding, maybe 11 gigahertz in combination with 6, we can do that, with 1 indoor unit and potentially one antenna as well. So summary. Again, I just wanted to, summarize with the portfolio that's involved. Any one of these indoor units can play a role in the multiband booster solution. So you're not necessarily selecting the indoor unit based on whether it can do this or not. The reason for selecting the indoor unit really has to do with the number of directions you're terminating at a particular site. But each one of these can do that. We can talk about the specifics of your particular opportunity. The radios, traditional band radios, are 6363 and 6365. I didn't talk about this one, but this one is actually a dual carrier radio that is being released here in the second half of this year. 18 gigahertz is already available, or will be available this quarter. And then other capacities are coming on along, or other bands are coming along here in the months to follow. And then the outdoor solutions, whether it's the outdoor baseband 6366 or the all outdoor radios, E-band radio 6352 or the 6351, could all play a role and participate in this. Now, what's maybe interesting and what I really wanted to bring to this audience was two immediate opportunities for multiband. Now, Ericsson, because of what I showed here on this slide here before, this isn't our complete portfolio, but it does cover all of the bands, and both split mount and all outdoor. So we have the ability to do either part of the multiband solution, whether it's the traditional band or the E-band, and more importantly, we have the ability to combine them with a policy-based forwarding solution in the indoor units. So where you may see an opportunity here with your customers is basically layering on Ericsson onto an existing deployment. For example, if you have an existing E-band deployment that maybe isn't performing so well because they've just stretched the range too far, and you're not getting many nines at all. Well, if you layered on an Ericsson 18 or 23 gigahertz link in parallel and then added a dual band antenna, then you're effectively going to deliver a solution that'll give you better availability for the same footprint, and now you can direct the traffic to the appropriate link. And then similarly, if you have an existing solution, whether at a traditional band, at a lower band link that needs additional capacity, then of course adding on the Ericsson 80 gig solution, in combination with multiband booster would give you that additional capacity, same footprint, and then again the ability to direct that traffic to the appropriate link. So I think those are maybe some teasers that maybe help you think about some ways to get started with multiband booster. Obviously, it's a very clean and cohesive solution when it's all Ericsson, but that doesn't mean that it has to be all Ericsson, and we can work with existing deployments either way. So as a summary, multiband booster is kind of that, it's an innovative solution for delivering increased capacity and performance for existing links. So giving you, again, the best of both worlds. So delivering high capacity at longer ranges. There's a TCO chart here that basically shows that with a solution like multiband booster, we can kind of keep the operating expense, actually the Gbps expense, sorry, fairly flat, and it only kind of increases when we need to add radios essentially. Some additional areas for reading. We have a couple of different publications. First of all, the Ericsson Technology Review, where back in 2016 is when we introduced this concept, made basically with two lower bands, but when we added the E-band product, then that was obviously becomes a much stronger solution. So those articles are outlined here. And then the Ericsson Microwave Outlook is an annual publication that we make that talks about the where we see the state of the microwave business overall, not just Ericsson's, but how our operator customers are using microwave and deploying it, and where we see it going in the future, as well as usually some peeks into the R&D. I highly encourage that because it's very fascinating. We've got R&D and even higher bands that the potential for further capacity enhancements is even greater. So it's very interesting reading. Just a few little facts and figures about Ericsson and microwave. If you aren't familiar, you're certainly welcome to use these facts and figures with any of your customers. We've been in the microwave business for over 40 years and have been a leader in that because typically our microwave solutions have followed the ramp up of wireless access of cellular networks. So we have well over 4 million radios deployed in that time. 880 customers, 180 countries, lots of R&D engineers all over the world, and a number of firsts in terms of references, including multiband booster. First with radio link bonding, well before that. MIMO, we've done MIMO demonstrations up to 138 gigabits per second over in Greece. That was early last year. We've done really long links over water. In this case, 2.3 gig over 128 kilometers. And then 100, yeah, this is the E-band and MIMO solution that I was talking about. So, we're constantly putting, our time and effort into developing microwave technology, and it shows in our products. So how do you start? Certainly, we already have a presence on the WENCOM website, which we kind of get a peek at here. If you have any questions, we have done lots of training and enablement activities with WENCOM. So we think we're ready to go. Talk to your WENCOM sales rep. There's a link here for a form here as well that you can use. And then here's a little peek at some of the content on the WENCOM site, on the Ericsson Mini site for WENCOM. So there's a number of papers. Here's the Ericsson Microwave Outlook. So you just need to go to the WENCOM site. You can find a link to the Ericsson Microwave Outlook there, as well as a number of other interesting topics. And time for Q&A. I hope this was a good topic, and I'm happy to take any of your questions, which unfortunately I can't see very well. Let me see if I can stretch this. Elaine, can you maybe walk me through the questions? I see that there are some, but.
Yeah, so there's a couple more. Which mix of frequencies are available?
I'm assuming this is for the